Today's my topic is presenting graph and graph isomorphism. So how to present a graph? How to represent a graph? For representing graphs, first we discuss about adjacency list that specifies the vertices adjacent with each vertex in a simple graph. It can be used for a derived graph as well as a list with terminal vertices adjacent from the each vertex. Consider the following graph having with 5 vertices and 5 edges. So we can say the vertex A, vertex B, vertex C, vertex D, vertex E. And the corresponding adjacent vertices for A is now C and D, because C and D are incident on this vertex A. Similarly, we can check the adjacent vertices for D are A, again C is adjacent with D and E is adjacent with D. So just you see this tabular form, C and D are adjacent with on vertex A, E is adjacent on vertex B, A and D are adjacent on vertex C, A, C and E are adjacent on D, D and B are adjacent on E. How to represent a graphs? So adjacency matrix. What is the definition of adjacency matrix? The adjacency matrix is n by n, that is a square matrix. It's a 0, 1 matrix with 1 representing its adjacency and 0 representing its non-adjacency. Therefore, it is always a square matrix. Adjacency matrix of a graph is based on the ordering of a vertices. For a graph with n vertices, there are n factorial adjacent matrices. Adjacency matrix of a graph with few edges is a sparse matrix, many zeros and few ones may be possible. Now we'll talk about how to find adjacency matrix of a simple graph. So for that graph, we required to choose a simple graph and then we'll design its adjacency matrix. Let us take again same example of previous slides. Suppose this is a graph with 5 vertices. Then if we label the vertices with A, B, C, D, E as ordering, it's now your choice. So corresponding adjacency matrix can be written as this 0, 1 matrix. So we can say the rows and columns indicating by these vertices. So there is no edge from A to A, that's why this is entry for 0. So we can say this is A, B, C, D, E, or this A, B, C, D, E. If you are labeling the rows and columns for this adjacency matrix. Now, you can check there is no edge between A to B. That means B is not adjacent with A. Therefore, we can get entries now 0. But we can easily say the vertices C and D are incident on A. Therefore, we can get entry in this adjacency matrix is now 1, 1. Now the vertex E is not adjacent with respect to A. That's why this entry is now 0. And you similarly found that the exact entry which you are taken in rows that you can found in columns, that's why it's a symmetric matrix. So this is a adjacency matrix of the corresponding graph of size of order is 5 by 5. Now we discuss about the adjacency matrices for multigraphs and the pseudographs. With multiple edges, matrix is no longer 0, 1. If more than one edge exists, the list of number of edges can be taken. A loop is represented with a 1 in its positions I to I. Adjacency matrices for a simple graph, including multigraphs and pseudographs, are again symmetric. Adjacency matrices and the digraphs. So for derived graph, the adjacency matrix has 1 in its ith position if there is an edge from Vi to Vj. Derived multigraph can be represented by placing the number of edges in positions ij that exist from Vi to Vj. Adjacency matrices for digraphs are not necessarily symmetric. What is incidence matrix? In an incidence matrix, both rows and columns represent vertices. In an incidence matrix, rows represents vertices while column represents edges. A 1 in any matrix positions means the edge in that column is incident with the vertex in that row. So we will take entry 1 if that an edge is incident on that vertex. Multiple edges are represented identical columns depicting the edges. For example, the incidence matrix of a graph. Suppose this is a graph. Now how to find its incidence matrix? The row contains vertices and column contains edges. So we can say, suppose this is an edge E1 from A to E, and E1 is adjacent, E1 is incident on the vertex A. So there is entry 1. E2 is also incident on vertex A, E3 is also incident on vertex A, E4 is also incident on vertex A. Therefore, we get in incidence matrix entries 1, 1, 1, 1. Now, none of the other edge is incident on vertex A. That's why we can get the entries now 0, 0, 0, 0. Similarly, we can check for B. The edge E6 is also available on B, and edge E5 is also available on B. That's why there is a entry is now 1, 1. So we can check all entries for the remaining vertices. What is graph isomorphism? The simple graph Z1 with vertex set V1 and edge set E1 and the graph Z2 with vertex set V2 and edge set E2 are isomorphic if there is a 1-to-1 and onto function f from V1 to V2 with vertices A and B adjacent in Z1 if and only if the corresponding images, that is f of A and f of B, are adjacent in Z2. This is true for all vertices in A, B in the graph Z1. Function f is called an isomorphism if determine the isomorphism. For that, some conditions should be satisfied. The number of vertices, the number of edges, and degrees of vertices are invariants under the isomorphism. If any of these quantities differ in two simple graphs, we strictly say that, or we immediately say that the graphs are not isomorphic. If these quantities are the same, then the graphs may or may not be isomorphic. To show that a function f from vertex set of graph Z to vertex set of graph H is an isomorphism, we need to show that f preserves the edges. The adjacency matrices can help with this problem. We can show that the adjacency matrix of Z is the same as adjacency matrix of H when rows and columns are arranged according to F. For example, consider the following two graphs. We observe that the graph Z and H having 6 vertices and 7 edges. In graph Z, the vertices labeled are U1, U2, U3, U4, U5, U6. In graph H, the vertices labeled as V1, V2, V3, V4, V5, V6. So these both graphs having 6 vertices and 7 edges. Both graphs have 4 vertices of degree 2. We can say this one degree 2, this one degree 2, this is 2, this is 2, or this is 2, and 2 vertices of degree 3. Sorry, U4 and U2 are degree 3, and U1, U5, U6, U3 are degree 2. Here we can also observe that the vertices V1, V2, V6, V4 of degree 2 and V5 and V3 of degree 3. The subgraph Z and H consisting of vertices of degree 2 and the edges connecting them are isomorphic. So if we consider any subgraph underlying with these vertices and edges, we can easily show that they are isomorphic to each other. We need to define a function f and then determine whether or not it is an isomorphism for the graph Z and H. Degree of U1 in Z is now 2, and U1 is not adjacent to any other degree 2 vertex. So we can observe that U1 is adjacent with degree 3 and U1 is adjacent with degree 3 as vertices U2 and U4 respectively. So The image of U1 must be either, if we consider the graph in H, is either V4, because V4, you can get it, or V6. Okay. Can arbitrarily set f of U1 is equal to V6. If that doesn't work, we can also try for V4, no problem. Continue with these definitions for that graph. So see, since U2 is adjacent to U1, the possible images of U2 are V3 and V5. So we can set f of U2 is equal to V3, again arbitrarily chosen. Continuing in this way, using adjacency and degree of vertices as guides, we derive f for all vertices in Z as shown in next slide. Suppose we define this mapping in this way. F of U1 is equal to V6. F of U2 is equal to V3. F of U3 is equal to V4. F of U4 is equal to V5. F of U5 is equal to V1 and f of U6 is equal to V2. So we can get this mapping preserves one-to-one and onto relations. So next we set up an adjacency matrices for graph Z and for graph H, and arranging the matrix for H so that the image of Z vertices line up with their corresponding vertices. So we'll again consider same graphs. Suppose this is a adjacency matrix of a graph Z and this is adjacency matrix of a graph H, and we observe that both matrices are